Just to recap that what we are discussing the major and minor losses in pipe flow. So at the moment will start with the major losses, and then we will move on to minor losses afterwards. So uh, the equation which we derived by the comparison of energy equation with the Bernoulli equation that is written here in form of a head. So we know that we can define pressure head and dynamic head, then elevation head, and then here the term HS that is given by shaft work head. So it would be positive when we have got turbine work output, and it would be negative when we are talking about pump work input. So that is in terms of head. So that shaft work head can be defined by the shaft net input work rate of that net input work divided by m dot, which is mass flow rate, and g, which is gravitational constant. And that, because we know that m dot is rho uh, into volume, so then we can of course write rho into g. M dot is rho into volume flow rate. So rho into g is the specific weight, which is gamma, and that volume flow rate is taken here. Now the last term in the equation, which is HF. So that is the losses uh, which the flow encounters in a piping system. So now these losses can be divided into two categories. One is called major losses. So that is due to friction or the viscous effect in the straight pipe, and then minor losses which are due to those various component of piping systems like elbow steel valve and bends, sudden contraction, sudden expansion, flow coming in from a reservoir, flow going into reservoir. So there are many types of discontinuities in piping system. So after that, we discussed that if we have got turbulent flow in a straight pipe, because we are talking about major losses, so we will only consider the flow through straight pipe. So in that, we need to have some need to consider surface roughness as well, because for the turbulent flows, as we discussed in the last class, that flow that pipe surface roughness also becomes very important parameter. So in this flow, the critical parameter which we want to determine, that is pressure drop, and that is function of velocity, diameter, length, and surface roughness, which is epsilon, which is the force parameter on the right hand side, and then these two fluid properties, which are viscosity and density. So if we apply the dimensional analysis, we can come up with this form, which is down-dimensional pi terms. So now we know that L upon D is directly proportional to delta P, so we take it out of that functional form because that is directly proportional. So we write it like this, and then delta P upon half rho V. Delta P is related with the friction factor by the relation F is equal to delta P into D upon L divided by rho V square upon 2. So that is we discussed in the last class in detail, and then when we put this from here, if we put the value of delta P in this equation, so that would be equal to F into L upon D into rho V square upon 2, and then if we do the simplification as we did in the last class on the whiteboard, we can come up with the relation that the friction factor is function of Reynolds number and relative roughness. This epsilon upon d is the relative roughness of the pipe. So in the laminar pipe flow, that friction factor is only dependent upon Reynolds number, and that relation was 64 divided by Reynolds number. But for the turbulent flow, as we discussed, that because the viscous region shrinks towards the pipe surface, and the pipe and the velocity in the near pipe surface region becomes very disturbed by the surface roughness. So that's why we consider surface roughness in case of turbulence. Right. So up to now we have determined that friction factor is function of Reynolds number and the relative roughness. Now, if we consider, now we with this brief recap, let me go to the whiteboard. Now we consider a pipe section which is one end, right? So here if we want to write the energy equation between these 2 points, we know that we can write by P1 in terms of head, P1 upon gamma plus V1 square upon 2G, which is the dynamic head. This is pressure head at point 1 plus Z1 is equal to P2 upon gamma plus V2 square upon 2G plus Z2 plus HL. HL is the loss in which this fluid experience, loss of head which this fluid experience due to friction and any component. So because this is a straight pipe, there is no component. So here HL is only the loss due to frictional effect. So uh, now if we are talking about fully developed flow, then we know fully developed pipe flow, then we know from the continuity equation that V1 is equal to V2, and if it is a horizontal pipe, so it means that there is no elevation difference, then we can say Z1 is equal to Z2. Right. So if we do the simplification here, so V1 and V2 head, that velocity head is the same and elevation head is the same. So we can write P1 upon gamma is equal to P2 upon gamma plus HI. So from here we can say that P1 minus P2, which is delta P, that is equal to gamma into HL. So we all know that gamma is specific weight, and that is equal to rho into volume, right? So we know it from our fluid mechanics 1 knowledge. So now this delta P can also be written in terms of friction factor, as we discussed in the previous class. That if I take you back here.
सॉरी ये एचएल कहाँ से आ गया था ये क्वेश्चन ड्राइव किया था
Okay. This HL. Okay. Please, can you please tell me your name and let me see. Umair
सॉरी भाई
Khalid. Umair Khalid. Okay. Umair, if I take you back, here we in the last class, if you remember that we wrote it in by the comparison of energy equation with the Bernoulli equation. We wrote these two equations, and if we compare these two equations, if we look closely, the above one is the energy equation, the first equation, and the second equation is the Bernoulli equation. Right? Bernoulli equation is the equation which you studied in FM1, and energy equation, that is 5.33 section, which I told you to read in the book in chapter 5. So if you see that the left hand side is equal to the left hand side of both equations are equal. On the right hand side, the first three terms are equal, and the only term which is appearing, the additional term, that is this term, minus u out minus u in minus q net in. So that is the term which is included in the energy equation due to frictional effects. Otherwise, if there is no friction, then this term wouldn't be there, as it is evident from the Bernoulli equation. So it means that if there is a friction, then at the uh, at the outlet of the pipe, energy would be a little bit less. That the energy head, which is the mechanical energy head, which is available in the fluid, that would be less because of the friction. Because due to friction, some of the mechanical energy is converted into thermal energy. So that loss is written here, right? And now if we, Umair Khalid, do you understand up till this point?
Yes, sir.
Okay, now if we divide this equation with the gravitational constant, which is, I think, let me, so I have written it again. So if we divide it by the gravitational constant, then we can write it in terms of head. Now we have written the energy equation in form of head, pressure head, velocity head, and elevation head. Now there are two additional terms which are appearing on the right hand side. One is the shaft work head, and the second term is the loss head due to friction and those components. So because this HS is the shaft head, shaft work head, and this HL is the loss head. Now this loss head has got two components. One is the major loss head component, which is due to friction, and HL minor is the minor loss head component, which is due to a different component. So that is written here. Now we are going to discuss this friction loss head and this component loss head, which are major and minor loss head components, uh, one by one. So for the major loss component, we are only considering the turbulent pipe flow through a straight pipe, right? So it means that there would be only a minus HL, and we are not talking about HS, which is the shaft head added or subtracted due to the turbine or pump, right? Umair Khalid, are you with me up to this point?
Yes, sir.
Okay, so after that, I have written that equation here. That P1, because in this equation, this was P2, 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 and Z2. So this HL, when it goes on the left hand side, it would be added plus HL. And this was P1, P1, and Z1, right? So that's why we have written this equation here. That P1 plus V1 plus Z1 is equal to P2, this pressure head plus V2 plus and V2 plus HL. So now we want to write this HL in terms of this friction factor. So we also know delta V is equal to FL upon D, rho V square upon 2. So now we can also know delta V is equal to gamma HL. So let me derive the relation between friction factor and HL on the whiteboard. So let me write that here. Okay, before Umair's question, we were trying to discuss that from where this relation came. So let me take you back on the previous slide, one of the previous slides. here you can see that delta P is equal to FL upon D rho V square upon 2. So let me take you back to this current slide. So now we are going to do it on the whiteboard. So let me write that delta P is equal to F length upon diameter into rho V square upon 2. Now this delta P and this delta P, they are equal, so we can say that gamma HL is equal to FL upon D rho V square upon. From here, if we know that this is equal to, it is now gamma is rho G, sorry, it was, you should have told me that I have, so it is basically, because rho into volume is mass, so it is rho G, specific weight. So if we put that value here, rho into G into HL, FL upon D, rho V square upon 2. So from here, rho would be cancelled out, and HL would be equal to F L upon dV V square upon 2. So this is the relation between minor this major loss major head loss and the friction factor. Now the friction factor for the laminar flow, we know that that is equal to 64 upon Reynolds number if the flow is laminar, and for the turbulent flow, as we discussed from the dimensional analysis, that it is function of Reynolds number and relative roughness, right? So, but this is a functional form. We don't know the exact relation in case of turbulent fully developed flow. So, as we discussed that we for the turbulent flow we conduct experiments, and a person named whose name was called Moody. So that was the scientist name. He conducted experiments in 1944 to derive the friction factor for different Reynolds number for different surface roughness element, relative surface roughness values, and he come up with Moody charts. So let me show those Moody charts to you on the next slide. So that are here, and so let me zoom in just to tell you that what are these Moody charts. So if you see, first of all, this chart is on a log scale, right? So we can see that on the x-axis we have got log scale, because there are a vast range of Reynolds number to cover, so that's why we have put the log scale. And similarly, there is a vast range of that surface roughness, relative surface prediction factor, and surface roughness. So that's why the y-axis is also in the uh, in kind of it is if we see that y-axis is normal scale, but the x-axis is kind of log scale, or am I right? 0.04 and 0.03. It looks like log scale as well, or no? No, it is normal scale. Okay, so now if you see that there is a line on the left hand side, which is a linear line. So that is kind of the line which is due to due to laminar flow. That is the line which covers 64 upon Reynolds number, and then there are several lines on the right hand side, and we have got a value written in front of each line on the right hand side. So these values are for the relative roughness, which is epsilon upon d. So epsilon upon d for the top line is 0.06, and then here on the bottom side we have got 0.00005, and then on the x-axis we have got Reynolds number value, which starts from 10,000 to 10 million, or maybe 100 million. So it goes up to 100 million, right? And then for this case, there is a bottom curve on the right hand side, which indicates smooth pi surface. It means that epsilon upon d value is equal to 0 for this case. So if we have got turbulent flow, and if we can ignore epsilon upon d value, then we are going to see the value from this curve. So let's suppose we have been given a smooth curve, and we have got Reynolds number of 1 lakh. Then we would draw a straight vertical line from this point, and then we will see that where it intersects this line, and from there we will draw a horizontal line to find out the value of this friction factor, which would be around, from this it would be around 0.02 0.018, around that value. And if we have got some other value of epsilon upon d, then we can draw a vertical line from that curve, and then we will find the intersection point, and from the intersection point we will draw the horizontal line. So we will also do a numerical problem for this in maybe in couple of minutes to elaborate it further. And okay, one thing which I want to also discuss here, that is there is a dotted line, this slanted slanted dotted line on the right hand side. So after this line, if you see that this curve, they almost become horizontal. So it means that after this point, friction factor is only function of surface roughness. That is no more Reynolds number dependence, because that becomes kind of horizontal line. So horizontal line means that if we change the x-axis, then there is no change in the friction factor value. So it means that after certain value of Reynolds number for each surface roughness value, that this friction factor only depends upon the surface roughness. So we can write here that this relation, that for this friction factor, sorry, this friction factor becomes only function of epsilon upon d for higher Reynolds number value. How much higher, that depends upon the particular surface roughness value. Because, for instance, if we are talking about relative roughness of 0.06, then after around 10,000, there is no change in friction factor value. So it means that for relative roughness of 0.06, 10,000 is the value of that high Reynolds number. But if we are talking about 0.005, 0.0005, which is this line, that value of higher Reynolds number is like 50 million Reynolds number value. So after that, it becomes independent of that Reynolds number. So that all depends upon the Reynolds number value. Reynolds number value for a particular surface roughness value. So this smoothie chart was given in I think 1944, and after that a scientist named Colebrook, because this is a semi-log scale, so it is very difficult to get the correct value of friction factor. So a scientist named Colebrook that gave us the relation for the non-laminar flow, pipe flow, which means transitional flow, and the turbulent flow, which are these curves which are on after this 4000 value. So for that he gave us the this relation from which we can calculate the friction factor value. So if you look to this relation carefully, you can see that this is an implicit relation. That friction factor is also occurring on the left hand side and as well as on the right hand side. So we need to have some kind of iterative solution, which we can do very easily on the programmable scientific calculators. And if you don't have that, then there is an explicit calculation of this friction factor, and here this is given here that friction factor is only appearing on the left hand side, and then on the right hand side we have got only epsilon upon d, which is the relative roughness and Reynolds number. So that is for the transitional and turbulent flows. So friction factor for laminar flow, that is 64 upon Reynolds number. For the transitional and turbulent flows, you can either use Moody chart or these two relations. One is implicit and one is explicit uh, relation, right? So I would suggest that you can use the explicit relation, because it is quite easy to do the calculation. But if you want to have more accurate value of friction factor, you can use implicit and this formula, and you don't need to memorize these formulas, so it could be available to you in the paper whenever that scenario occurs. So let's do a numerical problem to discuss the calculation of those friction factors. So here under standard conditions, the rho and mu value is given. Flow through a 4 mm diameter drawn tube. So this is a drawn tube. So that is a manufacturing process. So for that, the roughness value, surface roughness value, which is epsilon, that is 0.0015 mm. So let me write these values here. So first of all, I think rho is 1.23 kilogram per meter cube, and then we have got no, not 1.23. What is the value? It is 1.23, right? And then mu value is 1.79. 1.79 into 10 to the power minus 4 Newton second per meter square. And then we have got diameter is 4 mm. So diameter is 4 mm. So it can be written 0.004. Then epsilon value is 0.0015. So we have got epsilon value. Sorry. Epsilon value, that is 0.0015 meter. So if we want to calculate epsilon upon d, which is the relative surface roughness, that would be equal to 0.0015 divided by 0.004, and that would be equal to, if we use the calculator, then we can see that it is equal to 0.00037.5. Right. So up till here we have written the data, and then velocity is 50 meter square, 50 meter per second. Sorry, 50 meters per second. For such conditions, the flow would normally be turbulent. And the statement is saying that flow would be turbulent for these conditions, but we can take precautions to eliminate any disturbance to the flow, like the entrance to the tube is very smooth, the air is dust free, the tube does not vibrate. So there is a possibility that we can maintain the laminar flow even the Reynolds number range is in the turbulent flow. So if we calculate the Reynolds number value for this flow, that would be equal to rho v d upon mu. So if we put the value 1.23 and then d is 0.04, velocity is 50 meter per second, and mu is 1.79, 10 to the power minus 4 Newton second per meter square, its value comes out to be 13,700, and we know that is greater than 4,000. So in normal cases it would be always turbulent, but because the statement is saying that we can keep it laminar by removing the disturbances which would create turbulence, so that we need to determine the pressure drop in a zero point 0.1 meter section of the tube if the flow is laminar. So even though we know that it would be turbulent, but just in case if the flow is to be laminar for this particular Reynolds number, the statement is saying that we need to calculate the pressure drop uh, in in a section of tube which is zero point 0.1 meter long. So for that we can, if the flow is laminar, then F, which is friction factor, which that would be equal to 64 upon Reynolds number. Reynolds number value is 13,700, and if we put it here, we can calculate the value be equal to 0.00467, and then we know we just discussed that delta P is F L upon D rho v squared upon. So we know all the values, friction factor, length we know 0 0.1 meter, diameter 0.004, then rho value is given, velocity is given. So if we calculate that, that is 0.179, 0.179 kilopascal. So we can also say 179 pascal, or we can say 0.179 kilopascal. So that is the value of delta P, and that can also be the same value of delta P can calculated from the relation for the laminar pipe flow fully developed, which we determine that that is equal to 32 mu L V upon D square. So that is we also discussed in the last week's lecture, that all these derivations. So from this it would also come out to be 0.179 kilopascal. Now this was the part 1. Now the part 2 is determine repeat the calculation if the flow is turbulent, which it would be most definitely, because the value of Reynolds number is greater than critical Reynolds number, which is 4,000 or 2,000 per se. After 4,000, it is fully developed, fully turbulent flow. So in the range of 2,000 to 4,000, it is transition. So for the turbulent flow, we need to calculate F, which is friction factor. So now we have got two, three cases. Either we use this function of Reynolds number and epsilon upon d, and so we know that this would be the case. And either we can use the Moody chart, so we know epsilon upon d value is 0.000375. So now either we can use these relations or we can use this Moody chart. For instance, if we use this Moody chart, 0.000, I think 0. It is 0.000375. So 000375 would be somewhere here, right? And let me see, 0.001. No, it would be somewhere here, where the mouse cursor is, 000375, and Reynolds number would be somewhere 1370. It would be somewhere here, right? So you can see that it would be quite difficult to see the value because at this end of the table all the curves are kind of converging. So it is better that we use one of these two relations, but because the Reynolds number, as I explained, that is 13,000 13,700. So 13,700 would be somewhere here, right? And if we see all these curves are kind of quite jumbled up at this location, so it is very hard to see from this chart. So we can use these relations. So if we use these relations from here, the friction factor would come out to be 0. So if we use those Colebrook relations, we can find the value of friction factor. Uh, I am talking about these two relations. They are on the next slide. So we know epsilon upon, and let's suppose we use this relation epsilon upon d value is 0.000375. Reynolds number is 13,700. So if we put the values and do the calculation, so the f value, which is the friction factor value, that comes out to be 0.028. Now that is very interesting to see this value, that is 0.028, and for the laminar flow it was only 0.00467. So for the turbulent flow, friction factor value is significantly more. So now we are going to use the same relation, FL upon D, rho v square upon 2. So the only difference here is friction factor value. So if we put that value, then it comes out to be 1.076 kp, right? Because in the turbulent flow we also consider the surface factor, so that's why the friction factor is quite higher. And if you compare these two values, so the friction factor, the pressure drop for the turbulent flow, delta P upon laminar, so that would be 1.076 upon 0.179. So it would be almost 6 times. So it means that if the flow through pipe would be turbulent, then we need to install a pump which would have 6 times more pumping power as compared to the pump which is required for the laminar. Right? If all the flow conditions are the same, and the only difference is between the flow, if the flow is laminar or turbulent, then the pump specification goes quite high. if the flow is turbulent, which is kind of 6 times more if we want to achieve the same mass flow rate and for the given condition. So we need to provide kind of 6 times more pumping power, a pump which has got like, if for the laminar flow it was 10 horsepower, for the turbulent flow it would be 60 horsepower pump required. Right. So this was it uh, for the cases of major losses, and we have only calculated the friction factor, but we can easily calculate here the major loss for this. If we know the friction factor, we know the length, and then all other things are known. So let's suppose that for the turbulent flow we want to calculate the major loss, then friction factor we know 0.028, length 0.1 meter, diameter is 0.004, velocity is 50 meter, gravitational constant 9.81. So we can easily calculate the major loss as well, right? And we will do quite a few numericals in the next week for the major losses and minor losses. So minor losses would be discussed in the next class, which is on the Wednesday. So let me download the attendance. If you have got any question, you can ask. Otherwise, I think the class time is over. So let me know if there is any question. Otherwise, we can just finish today's lecture. So I hope to